thank you all of you coming. I would like to introduce Jens Fussing, who is from a consulting company in Denmark called COWI. Jens will tell us a little bit about how to build high-rise buildings, and I think I will let him introduce himself. So thank you to Jens.
Yeah, my name is Jens Fussing. I'm a structural engineer, educated about 21 years ago, but still very passionate about being a structural engineer. I'll just explain a little bit about myself first before we jump into the the presentation itself. Today I will say a lot of things about technical things, about opinions. A lot of the things I will say today will be my own opinions, because I will be putting up some slides of some different towers. Some of the towers I have not been involved with, but I have been, you can say, inspired by them. Some of them I know a lot about. So when I use the word we, it does not mean that it is absolutely COWI, because I have been in 3 different companies over the last 12 years. So it'll just go a little bit fast. And it doesn't mean that here comes COWI and say this is how the world is. So if you disagree with me, it's my opinion, a lot of the things which I'm going to tell about today. About 12 years ago, I was contacted by a company in Dubai who asked me if I wanted to be the, in-house consultant of a precast company. And I took that challenge. This was before, you can say, the actual boom of the Middle East. Even before that, I'm also educated carpenter, and I have worked in the States as a carpenter. And even in my childhood, when we go back again, I grew up in North Africa. So I have used a lot of my life outside of Denmark. I have now been back in Denmark for 4 years, and I'll say 50% of the work which I'm involved with is international. So 50% Denmark and 50% outside Denmark. And of course, a lot of the things which I'm thinking about, and the reason why I come here today is because when you are asked to give these presentations, you have to reflect on how do we build in Denmark and how do we do it outside Denmark. And of course, I would like to give you a pep talk, hopefully an inspiration for go out into the world and get knowledge, because that's what Denmark needs in the future. In the Middle East itself, I was involved with about 16 towers, and then for the last 4 years, I've been involved with 8 towers here outside and inside Denmark. So that's sort of, the first presentation. What I would like to just say is that when you go out into the world and you have a Danish mindset, then there are synergies, right? We come with something from Denmark, which is good outside, and then there are a lot of things which is good outside of Denmark, which we can then bring back to Denmark. That is the synergies when you exchange knowledge. So if you always sit in one part of the world and you always sit in Denmark, you will think like everybody else in Denmark. I think Hans Christian Andersen wrote a little fairy tale called The Ugly Duckling, where he describes this little way of looking at life. So that's why it's important to get inspired and go and see how everybody else does it. A lot of people, they say to me, this going to Dubai, that was so easy because there's so much money and it was not really anything. All these, ignorance and preconceived ideas, it's wrong. It was not like that. It was exactly the opposite. Because the Middle East was like a flypaper for the rest of the world. So all the consultants and all the contractors around the world went to the Middle East in the boom time. And the competition was extremely tough. If you didn't innovate, if you didn't adapt, then you were out of the market. So you constantly have to go with a paranoia in the back of your mind and find out how can we do things better? How can we optimize better than other techniques? So being in an environment where you constantly have to walk around thinking like this creates innovation and new way of building. So for example, this picture here is two small buildings where you can see you come with some Danish knowledge, which of course in this case is precast industry, precast building systems. But in the same time, you can see there's also some Arabic architecture included. Again, you have to adapt to where you are to survive. So my encouragement to you is to, at least you who are from Denmark, you will have to work for the next 40 to 45 years and have fun, right? Don't become like everybody else. Go and have fun and keep on to your dream, whatever dream it is, you have to explore it. Don't sit 10 years from now and look back and say, why didn't I do anything? Just stick on to your dream and then a lot of things will happen. Make things happen instead of wait of things happen. Say yes to challenges. Say yes to changes. That is the reason why I'm here today, to try to inspire you with these things here. When it comes to tall buildings itself, then you can, of course, you can say, in the old days, what did you use tall buildings for? But that was usually watchtowers and clock towers and control towers and churches and mosques and and also the Eiffel Tower. Whereas today you can say, in the last, if you look back in history and say, the tallest structure which was man-made about 3 years ago was the pyramids. And that height record was not broken before in the 1600s. I think it was in England, there is a church over there which broke that record. And then again, you have to move a couple of 100 years more, and then you have the high-rise in America, you have the Eiffel Tower, you have all these things coming. And now we see every other year that the height records are actually broken. But usually what are high-rise, if you look in the last 50 to 100 years, you can say high-rise is usually a landmark. And it's usually also structures which is happening in regions of the world where there is a huge economically growth. Right? If you take the States 100 to 50 years ago, that was where all the tall buildings was built. Then there was a boom in Southeast Asia, which went down to Australia, which then came back to Middle East, and now it's India and China. So all these places where you can see the economical growth, that's also where we built tall. And of course, also you can also say that the invention of the elevator also helped a lot on the tall buildings. If you want to read about the definition about what is a tall building, how do you define it from what should we say? They have something called architectural topping and structural topping, and all the definitions about how do you define a tall building. Then there is a federation called CTBUH, which is the only high-rise federation I know of, and they have all this described in these books here. They have a yearbook, and then they have four what should we say, smaller books every year with a ton of statistical material. A lot of these slides will include a lot of those. So if you want to read about the definitions, I recommend that you get these books here. You can look at them in the break here. If we jump into, of course, when you do high-rise buildings, then a great part of the the innovation is the structures. Right, you cannot build a tall building on mechanical installations. You have to innovate and you have to develop structural systems when you build taller and taller. So there are some fundamental things which you need to be aware of and look at. Again, if we go back to the pyramids and the churches in the 1600s, everything was all the structural system was bricks, with arc, using the arcing action. Then when you come up to the industrial age in the 1800 Eiffel Tower in the States, you shift it over to steel structures. Then the latest shift, which you can see here on this slide here, is that the blue one, what they have done in CTBUH is they have taken the 100, I think it's the 100 most tallest tower in each decade, and found out what type of material did they actually use. And you can see the first column in each of these is steel. So the blue first one, that's steel towers. And on the other side, you can see it says steel, concrete, composite, and mixed. So of course what you can see is that 50 years ago, all towers were steel structures. And then in the last 10 years, it has shifted over to become more concrete, or what is called composite buildings, which is a mix of concrete and steel. The reason for this is that now we can we can pump concrete up to 600 meters. That's what's done on Burj Khalif. We can model concrete behavior in our fine elements. It has a good damping property. We can do high strength concrete. It requires no fireproofing, which is man-hour cost on site. So this is the development which has happened over the last 10, 15 years. This shift in construction material. So of course that means that you should, when you start setting out a tower, you should know this. This is how it is. A little paradox is that, I don't know if you have seen this video on YouTube where these Chinese guys built this 40-story tower in 15 days. That is a pure steel tower, but it's all prefabricated. So anyway, there's always some fun to look at on YouTube. But again, it was the Chinese who did it. It was not Europe, it was not Denmark, it was not America. It was all developed in China. So what we also need to be aware of is that as we go up in levels on a structure, this first slide over here, the first curve, is from an old American construction book, Anlægstechnik. Here they have taken the towers, which was built in the 50s up to the 80s, and tried to categorize it, and found out how much material consumption do you use as you go up in height. And what you can see is, it's a dimensionless, what should we say, y-axis. But it tells you that, for example, if you go from 20 to 80 floors, you can see 20 and 80 floors out, that you will have to use 4 times as much material, approximately, per square meter. You take all the construction material and you divide it by area. Then you can see you have to use about 4 times as much. If you go to the second curve, this is developed by a company called Dar al-Handasa, an Arabic consultant. It's a little bit the same, but this is only for concrete towers. They have done this in-house study and found out that when you do again the same from 20 to 80 stories, then it's only 70% more material you have to use per square meter. So again, the shift over towards concrete is more preferable. And what you also can see when you have 0 levels, what is costing all the building? That is the horizontals. I mean, this slab and that roof. That is what is costing most. So as a structural engineer, when you set out your building, of course you should not have too long spans, because then everything becomes too heavy, too expensive, and all your columns and your core walls get punished afterwards. So these are the facts which we know about. The last curve is from Germany, where in Frankfurt, where they have measured a lot of high-rise buildings there, and they have said, somebody have thought, okay, if I build a 1-story house and the carpenter have to go every day and do his job, how much time does that take? okay, if he has to go and do that on level 10, 15, 20, how efficient is all the man-hour cost on site? So they have plotted this curve in. Of course, we can discuss is this correct or not. But what we can see is that it is less effective to build up in terms of man-hour cost, because you have to go up and down and get materials in and out. So these are just the facts which is there when it comes to structures and high-rise. Then, in terms of mechanical installations, MEP, it's the same. What should we say? It's the same pattern. This is Davis Langdon, who is a project management company, who have done this study where they have said if the blue one is symbolizing a 15-story tower, and then they say, and they use that as a benchmark and say, I know for a 15-story tower, how much does my mechanical installations cost? Then you can see when you double the size to 30 stories, 45, your unit rate of mechanical installations grows. And you can also see that it's actually less efficient. That's the red one, which is dropping, nyttegraden. So again, these are the facts. We have to live with that when we build tall. When it comes to high-rise structures, we also need to know about what is the distribution between the economy for the building. How much goes for structures, how much goes for facades, how much goes for mechanical installations and for finishes and elevators. Usually it's about 25 to 30% for the structures, for the facade and for the MEP. So when we sit and do high-rise buildings, and if we can see these key figures are going up or down, if it goes down, then we have really optimized. If it goes up, something's wrong. So we need to think about this, how it's good to have these key figures in the back of your mind. And I would also say in the future, for whatever job you have, you should always go back and reflect on what did you do on the last job, or what can be done better. The last curves here is where they have compared, this is also from CTBUH, where they have compared average square meter cost for a low-rise building and a high-rise building. I think this is from London, these two curves here. So, you can say, so now we can just go home because everything is too expensive. You use too much material, we use too much energy, and we have higher operation costs. So what can we do about that? This is what fascinates me about high-rise, is that you really have to think. You cannot just do as you have always done. You have to think new, and you have to try to improve the way you used to do it. For example, this with the spans. Don't take too long spans. Get a good set out. I'll show a lot of examples of this later on, how to do it. Get out to see the world. Get inspired. Use known solutions. And also try to develop on further. But I'll try to come back now about say, okay, why does it then make sense to build tall? We know this, so now we can just go home and sleep because it's impossible. Or we can say, okay, then what is actually happening? Why is tall buildings actually being built all over the world? And how can that be economical and how can it be sustainable? I'll just show you this picture here because I was asked to reflect on high-rise and on Denmark. If you can see the, what should we say, the little presentation from the beginning, what are we going to talk about today? And I'm actually glad that I got this question because then you can say, okay, what are the signs in the time? What are we seeing right now in Denmark? I think the last real tall building in Denmark was built in 60s or 70s. And then there was one out in Ørestad, this Færing. And then nothing really happened until a couple of years ago, where some other high-rise was finished in Denmark. But what we see everywhere in all the municipalities is that all town planning is now what can we say, identifying areas, zones, where they're actually allowed to build taller. There are many projects out there now in Denmark, which is under development right now. So we might read in the literature that there's a lot of, what shall we say, hard feelings against tall buildings, but the signs are the opposite. It's actually becoming more and more acknowledged. What I often hear is that the reason why I have write this, how do you feel? Because a lot of people think that that high-rise buildings are ugly, and they look, they smash the city. But does this one look ugly? I took this picture in downtown Baku in Azerbaijan, with these 3 towers in the background. Of course, if you think this looks ugly, then you might as well just walk out again, because this is what we have to do. We have to think it has to fit into the city. That is our responsibility as engineers and architects. So of course you have to reflect about this. How do we then make it so it makes a purpose? So if we then just go a little out in the helicopter and look at what is happening in the world right now, what is happening is that many things is happening, and that is that if you look at the first graph up here, you have the world map in 1950, and the small white dots are the cities in the world with a population more than 1 million people. Then underneath here you can see in 2015 how many cities do we then have with a population more than 1 million people. People, they migrate to cities. If you want to learn more about this, then of course you have to find that type of literature. There is this extremely good article in this one here, this National Geographic, where there's a lot of explanations to why do people move into the cities. There's a lot of references to other books which you can read and find out why is this happening. But the fact is, as engineers, we don't really care why it's happening. We just accept it. Okay, cities, they grow, and they will continue to grow. Again, look at the signs of the time. Isn't that what we're seeing here in Denmark right now? All of the outskirts are dying, houses are worth nothing, and people are moving to cities. It's happening all over the world in the same time. So it puts a lot of pressure on cities. Shanghai is growing with 10,000 people every week. So that puts a big demand on infrastructure and buildings. Anyway, so, and in the same time, population will also grow all over the world. There's a lot of discussions right now about how many people are going to be on the earth in the future. And if you have time, I can only encourage you to go to, again, YouTube and look at a presentation from Hans Rosling, who is a Swedish statistician who has done an extensive, research in human growth, population growth. And he has a funny little, story which he's looking at. He has one presentation which is called, a little bit provoking, it's called Population and Religion. A lot of people think that religion has to do with how many children you get. The conclusion is exactly opposite. That right now it looks like 80% of all women in the world are maximum getting 2 children. In the old 200, 300 years ago, you used to get 6 to 8 child per woman because 5 of them would die. This does not happen anymore. So the whole development is actually that the standard, number is about 2. In Denmark we are less than 2. So we're actually decreasing our population here. But we will still grow in population because people get older in our society. So his prediction is that in 2050, we will maximum go to 10 billion people in the world. But that's still 3 billion more than we are today. And of course, therefore, the politicians, the business, everybody needs to plan for this and say, okay, how do we then do this in the future? How is there going to be space for all of us? There was also another little funny or disturbing note in his presentation, is that 1 billion people lives in the slum actually today in all these big cities. The only place where the birth rate is more than 2 is actually only in a little bit in Bangladesh, Sub-Sahara, and then a few countries in America, South America. Otherwise, it's dropping all over the world. So, of course, the discussion is that if we have to be 10 billion people on the planet in the future, and we all want to live where the soil is fertile. We don't want to live in a mountain. We don't want to live where it's crap. So we have to live close to actually where we can produce food. And that is good with cities, right? Because then people move into cities, and we still have, what can we say, resources with fields, so we can grow food in the future. So of course the tendency is that, what should we say, that people will move to cities and cities will grow. And if you have to look at it from a sustainability point of view, then when you have tall cities, because you could take the city and then you could just splatter it out and say, if everything was horizontal, then we would also all have to go to work like this, right? But what happens when people come closer is that you get actually more effective. If you live close to where you work, if your children go to kindergarten very close to where you work, if all of this is correctly planned, then you can actually have a sustainable, what can we say, high-rise city. All this here is taken from this CTBUH conference from last year. There was also one 2012. I didn't go there, but the topic is still the same. How do you look at this in the future, that we can become more sustainable and effective, and still have food and all these people? If you take all the cities in the world and put them together, it's the same area as half of Australia. That's how much we are taking up of space today. Then you can say, okay, how much of that is actually water? How much of that area is actually useless? Poles, Greenland, North Siberia, a lot of areas you can't live there. So that's why that the cities is not stupid. It's actually quite good for the future if they are planned correctly. The biggest city right now is Tokyo, and there are 36 million people. There's another little example here. This is also from CTUBH, where they have taken, you can see this is the lower one is Burj Khalifa from Dubai, and then they have splattered it out in Chicago and say how much horizontal area would that be. And of course, first of all, you would use all that land, but also, what are you going to use it for? You're going to decentralize, because every little house up here will need to have their own telephone. They will need to have their own little carport. They will need to have a lot of things which is decentralized. So a lot of double work, you can say. So this is the discussion right now. What is actually the most effective way to plan the cities? I think now this is one of the aspects of why to build tall. Of course, Denmark, I don't think we'll build tall because we want some nice buildings. I don't think because we don't have that big pressure on the cities right now in size. But this is what is happening outside of Denmark. This is actually the reason why China is building all these suburbs only with high-rise buildings, is simply because the pressure on the cities is so big with population. If we then look at go into detail and say, okay, what is the difference between high-rise and low-rise buildings? Because that's usually the things we need to discuss. And again, in this book here, they also have all these definitions, the CTBUH. There's one definition where they say if your aspect ratio is more than 1:5, you can classify it as a high-rise tower. If it has more than 20 floors, that's another, what should we say, definition. if the building is so slender that it starts to be susceptible for dynamic loads. Usually you say if you have a frequency less than 1 hertz, then you need to look at dynamics. All these things are things which usually you can say this is how you classify a high-rise buildings. But there's a lot of things which these buildings have in common. And for example, because you build tall, of course, all your loads will become a lot bigger. So loads on foundations, on columns are bigger than for low-rise. Then you have fire engineering. In Denmark, there is a rule that says if you have to go more than 22 meters up, then you can actually, then the ladder from the fire department cannot reach anymore. So I think it's 45 meters in Germany. It's different all over the world. But the concept is that as soon as you reach over this limit, then all fire, or can we say evacuation, firefighting, all this has to happen with inside the tower. So let's say that there is a fire in the tower, then you still need to be able to run out of the building while there's a fire in the tower, and the stairwell needs to be secure. So that is how to understand the difference between high-rise and low-rise. Usually with these stairs is that the problem is with a high-rise building that nobody uses stairs in a high-rise building. Try to imagine when you have to walk more than 5 or 6 floors. Don't you always take the elevators? So nobody uses stairs in a high-rise building. So stairs is a waste of space. It's actually only there for the fire event. And usually they are pressurized so that, say that you have a fire, then there will be some alarms which will make sure that inside the well itself, there will also always be a surplus of pressure. So when you open the door, you will not get smoke in, but it will be pushed away. So everybody can run out safely. Then there is facade engineering. I'll show some slides in a little minute. What is the difference here? We also have always some funny structures where we need to build temporary structures. We have the vertical transportation. Let me just see, why did I put this one? Yeah, I'll just a few more on this with the cities. There's also in the CTBUH book here, they have you can actually see there's a world map. There's a lot of statistical material in all of these every time. Every time there's a new statistic topics. And engineers, we like to look at this. And then you can see where in the world have they built now the most high-rise buildings. So you can see where, and that's also the same places where the cities are growing. So it's a quite interesting stuff to read in. If we then go into the things here and say, okay, what is the difference between, for example, if we look at facade, why is this all of a sudden such a big difference between high-rise and low-rise? That's because buildings, they move, right? A little building does not move that much horizontally and up and down. But the high-rise buildings, they move. When there is an earthquake or a wind load, then the building will stand and move. Sometimes it will be in 2 directions at the same time. And they will also move this way because you will have different load on the different levels as you go up. Then you can also have what is called differential settlement. Say, for example, if you have one column in the corner, which is not as heavy loaded, and another column next to it, which is less loaded, but they're the same size, then you will have a differential settlement which will plant all the way up through the tower. So all these effects, and of course then also temperature and tolerances. So all these effects needs to be looked at. You need to detail all the detailing around how to fix your facade to the superstructure. I'll come back to some examples how we built here in Denmark and the challenges with this, because we built a little different than normal high-rise buildings. So this is a big issue. This has to be dealt with every time. And I say outside of Denmark, few Danish consultants has this called facade engineering. Facade engineering is a discipline and it has to be respected because there's a lot of things which need to be thought about. How to connect the walls, make sure that the fire, noise, everything is taken care of. Also, one thing which happens every time is that you need to think about how are you actually going to clean your windows. So usually on top of a lot of these towers, you will have what is called a BMU, a building maintenance unit. You can see them there on the top of these two towers, which will then go outside, and then you will have a cradle going down. And you have to think about it, because a lot of people say, I want the top, and I can have a big apartment up there. Okay, but you have to coordinate that with the BMUs. So from the beginning, think about it. You can see it on a lot of buildings around afterwards. All these things you can see, that's the BMU, there's everything. Another very, very important issue is what is called vertical transportation. I mean elevators. Because what is always the trick when you do high-rise buildings is the core size. You can see the core in the middle. What is driving the size of that? That's your stairs, your elevators, and your mechanical. That gives you a size of your core. And of course, if you can minimize the amount of elevators, you will, of course, minimize your size of your core, and you will have more sellable area on the floors. So what is always done on high-rise buildings is that you make what is called a vertical transportation study, which is like a traffic impact study, a little bit the same when you drive down and the queue starts to come and it gets red and it gets green and other cars comes, and you look at the peak. So for example, on some tower you can have, these super tall towers here, you can have maybe, let's say, hotel, residential, and office, or whatever. And they have different peak hours where people go in and out the building. So you actually do what is called a vertical transportation study to try to optimize the elevators and the amount of elevators and their sizes and their speed. Usually, I would say for smaller towers, say 20 to 30 stories, 4 meters per second is used in Scandinavia, but I would recommend that you go up to 7 and 8. What happens is when you go more than 7 to 8 meters per second, that is 8 meters per second, that is actually 2 floors per second as you go up. Is that you start to have a pressurized cabins, and that becomes a little more expensive. If you go to Dubai up into the Burj Khalifa, then there is a viewing platform where you can go up. It's about 460 meters up in the air, and it will take you 1 minute to go up there, which is 16 meters per second. So 4 floors every second. Then you're up there. The fastest elevator I have seen until now is one which is 19 meters per second. This is constantly being developed all over the world, especially in Southeast Asia. In Korea, it's actually, can't remember if it's Samsung or Hyundai, one of these companies, which have developed an elevator which can go 19 meters per second. If you could go to the internet after, there's a tower called Lotte Tower in Seoul, where they will use these elevators. So, and what is it when you stand and wait? When you stand and want to take an elevator, what determines if your experience is good, or if the elevator is good? It's actually just defined in waiting time. How long time do you have to stand and wait before that elevator comes? That is what drives all of this. And you say if it's more than 40 seconds, you start to get irritated and you walk away. So this is all what is put into this vertical transportation study. Then we have the mechanical strategy, which is all the mechanical installations. Air, plumbing, gas, heating, cooling, everything. I'm not a mechanical engineer, but of course there has to be a close dialogue between the structural engineer and also the mechanical engineer. There are different concepts which is usually decided on very early in the schematics stage, and that is the two first ones, where you say where do you want to put your main mechanical plant rooms, and in many towers you will see them in the bottom and in the top. In some other towers you will see them also with intermediate plant levels, and usually you say that level can go 10 floors up and 10 floors down. They serve that. Of course, the downside of that is that you cannot sell these areas in the middle. but it gives a very efficient, if you're a mechanical engineer, you will say this is the most efficient way to do your strategy. So it's always a trade-off between what is the cost of the mechanical and what can you sell. So a lot of optimization has to happen with all the shaft size over and over and over again until you know that you have actually made them as small as possible. If we then come back to structural engineering a little bit more again here, then one thing which is always very, very, what shall we say, important when we do high-rise buildings, that is to understand what is happening with the wind. And in the top there you can see some sketches about what typically happens on tall buildings when the wind hits the building. You have this effect that the wind will come down and you will have this turbulence. In some books it's called a downwash effect. So that's just how it works. And so what is always done is you will make a what's it called, a desktop study about, you can do this in a computer model, finding out how is the wind environment around the building. Where should you not put your door out of the building? Where is it good to do it? Where is it good to have a balcony? All this depending on the local wind environment. Then you have actual wind tunnel testing, which is done every time, every single time. Because first of all, you want to know what's actually happening with this geometry of the building. Second of all, the results from a wind tunnel test will always be about 25% less than what is prescribed in the codes. So there is also a benefit by doing this. Then of course the wind engineer will also help us with the comfort criteria, the accelerations in the top of the tower. They will also give us, because when you have such a huge building like this, or these different types, or whatever it is, if you just put the worst wind on all the facade, all the way around, then you will over-design a lot. So you want to have the correct wind pressures on your facade, so you don't do anything which is too costly. So what is usually done on these towers here is that if we look at Burj Khalifa there, the first one out here, people often say, what is the deflection criteria for a tower? How much can we allow in the codes that a tower can deflect? Actually, there is no requirement because what is the governing parameter for a tower? It's actually not getting seasick, right? It's the accelerations. And also if the building is twisting, then all of a sudden you can start getting seasick. The Burj Khalifa is moving 1.5 meters out to both sides, so it's 3 meters altogether, and you cannot feel it. You won't even sense it. So that's what happens to all of these buildings. But to get down to a practical level, then you will say 1/500 is your deflection criteria. If you look at earthquake engineering, we say 1/200. There is no limit like this. All in earthquake is that we have something called interstory drift, but that is close to being 1/200. So when you sit in the preliminary stage and you do your schemes and your concept, you will try to limit your structure to 1/500 for wind and 1/200 for earthquake. And what happens when the wind hits a tower like this? You can see this building with the clouds up there. That's for some islands. I think it's down from Tenerife. And when the wind hits the tower, then you will have these vortexes developing on the backside of the tower, and the tower will start to get into vibration. So we have to get a real dynamic analysis on this. So usually on the low practical level, what happens is that you talk to the wind engineer. He builds a model like this. Then you also give him your, your dynamic properties of the building. It's the stiffness, it's the masses. And then he will convert this into something we can use to design the building for afterwards. That's usually how it's done with wind engineers. And I actually like all these 3 towers because the first one, Burj Khalifa there, you can see all these, there are these emergency platforms where you can actually stand out, because in a fire event you will have what is called zone evacuation. So you can run down and stand on these safe platforms, and then you can run down again. But you can see the platforms are on different levels. The geometry is also different. So the wind cannot really get hold of the building. So all this vortex shading, this rytmisk hvirvelaflysning, is getting reduced. So they have actually minimized the impact from the wind by shaping the building. The same one on the one in the middle is Taipei 101. It was the same thing again. This is Thornton and Tomasetti who have done this. It's extremely interesting building to look at. But it's the same thing. You can see all the corners, they are chamfered off. So it's a little more aerodynamic. And when they did the straight one and the one with the chamfers in the wind tunnel test, they could actually reduce the wind on the building with 25% again, just by making it more aerodynamic. So of course there's a lot of discussions with what shall we say, wind tunnel people when we do the towers. So that's that one. When we go to further into the structures here, then I will say what is the fun about the high-rise and structures is that you really need to think about buildability. Every time you make a line or you decide something, it has a consequence 50 times or 40 times. So you have to really think about, is this the right solution for the whole building? And I'll just show some, but it's the usual things, right? When we have high-rise buildings, we always have a shoring, which is forward to build the foundations, slabs, columns, temporary structures. Just to a little mind teaser on the Burj Khalifa. When there is an earthquake and when there is a wind load, there is actually always tension in all members. There is no other way around. There is always compression everywhere. There is no tension in the building at all. I saw a statistic the other day that there's 150 towers in Dubai, which is built over the last 10 years. Again, I haven't seen one single tower which has any vertical post-tensioning. Not at all. It's only something we do here in Denmark. We can come back to why we're doing it. But again, it's a little bit better go out to see what is done in the world, get a grasp of how do they do it out there, and then bring it back home again afterwards. The usual thing when you have when you have towers is that you have very big loads on your foundations. You can see the foundation, for example, up here where you can actually walk inside the foundation when you inspect your reinforcement. And you will always have board piles. I mean, a board pile, which is, let's say, 1 meter, 1.2 meter, can take 10 times as much as a Danish driven pile. And loads will be big. It will be 50,000 kilonewtons in the column. So if you have 50,000 kilonewtons in a column, and you take a Danish pile, you need 50 piles. Right? So that's why it's almost the board piles you use if the soil cannot take the load alone. This basement here is 6 stories deep, because again, it's about density of population. You will have many people there, therefore you will have many cars. So it's a thing which is there every time you do high-rise. You will have this with the basement and the car parks. Then we have the slabs, the concrete slabs, which can be, of course, be done like we do here in Denmark with TT slabs or hollow core slabs. But what is very popular is post-tension slabs, which is some bridge technology. Again, remember what I said in the beginning about synergies from different countries. You can also have different synergies between different services and skills. So if you take some bridge technology and put it inside a building and use it for your slabs, you can see up there the strands and the cables. You can actually have usually up to 8 meters in both directions. You can have a slab which is about 200 millimeters thick and no beams dropping down. So it means that you won't have anything increasing your floor-to-floor level when you have to look at the coordination with MEP. This is a very popular system for a lot of the buildings. When it comes to columns, it's a little bit the same again. It's the usual things we have, but one thing which is important to understand is that mostly all columns, especially in the bottom of the building, what is governing for calculating the size of the column? It's actually just compression. The moments are not that big. So you might as well just say, what is the compression? And then you find the size in the concept stage. And if you use these composite sections as an alternative to either concrete, then you can further decrease the size of your columns. Of course, they're a little bit more expensive, but you get more space. Now we come to some of the funny things about a high-rise, and that is transfer structures, which is just like building a bridge up in the air. Usually, because you have this transfer structure here, okay, that is just an architectural hold in the building. I don't think it has any purpose other than architectural. But you will have typically, what should we say, challenges in high-rises when you have mixed use. Say you have a car park in the bottom, then you have residential. What happens to all the columns when they go down into the ground? And maybe it'll screw up a whole car park. So transfer structures is a very, very typical high-rise phenomenon which we have to deal with. Usually the columns which are standing on top of a transfer structure is called a floating column. And how to model this is a trick, because I'll also come back to that in a minute, because your load and your stiffness will come as you build the structure. You cannot just build your computer model, turn it on with gravity, then your design forces will be wrong. So you have to get the program which can actually deal with this. That you model, it's just like building a bridge out, next, cantilever from both sides. When you then hit each other, then all of a sudden it gets another. Maybe it's pinned in the both ends, but you will have some stresses which is already there. So you need to have the correct software to model these things here. I'll just show you some funny ones here where we can say this is an architect who have drawn some lines on a drawing. This is just to show you the consequences of lines on a piece of paper, and then afterwards you have to build it. If you take the first one out there, it looks nice with this bridge hanging up there in the air, but I mean you have to build all this temporary scaffolding to carry the wet concrete while you are casting. And it's a little bit the same. You can see what's happened on the other tower here. And I'm sure that on the architectural drawing it looks nice with this little thing coming out here, this little building. It does look nice. You can see it afterwards there. But also in the same time, you can say, remember in the beginning we said it's expensive, it takes too much time, we have to think. For both of these towers here, you can say, see, what is the problem with this one, for example, is that, and also the first one, you see the car park which is there in the bottom. You cannot finish that before you come to the top of the tower. So it's just standing there and you can't finish on your time schedule. You cannot finish the building. And that is costing a lot of money. So of course what we have to do as engineers, this one here, I don't know the project, I don't know who have made it, but I'm sure that the contractor and the architect and the engineer are not best friends, right, since they have done this. Because there are methods how to solve this. See, you have these concrete beams coming out. When you come up to that point, you could just put a steel beam inside the concrete beam, which can carry the self-weight of the wet concrete, say 5 or 10 floors up. Then you could actually finish underneath and you could continue working on top. So that's where, we can make a difference when we go out and see this technique. This is done many places. I'll show another building where it's actually done like this. So to do things right, of course, will also help, first of all, to save a lot of money, but also to make high-rise more acknowledged. Here are some other examples of some transfer structures which are finished. one with the hole in the middle, and then there's one here at the harbor front where you can see a whole building standing on a huge transfer structure coming out there. The one with the hole in the middle is actually done in stages that what should we say, because it's a post-tension beam, the one with the hole in the middle. If you post-tension it for all the load, it will actually destroy. So it's post-tension in stages. When you start loaded, then you post-tension more and more and more. So when you come to the top, then it has the right stress level afterwards. A little bit like a bridge structure. There's a lot of similarities between, I'll say, bridges, tunnel, and marine, and the high-rise buildings. It's the same way to do the foundations. It's big concrete structures. It's a lot of similarities. I'll say some of the best high-rise contractors I have seen actually have a bridge education. So it comes easy for them to think big, and I think these dimensions here. C. Now I was told to reflect on Denmark. This is, I won't say where this is, but it's a shopping mall in Denmark. And you can see these columns here standing down in the car park. This structural engineer or client or whoever didn't know about a transfer structure. You can say, okay, maybe if this where we have these columns dumping down there, okay, what if a transfer structure had cost 2 million Danish crowns? So what? Right? You could have all these car parks. They all rented out these car parks here for 50 years. Right? So I'll say all these columns here, there should have been a transfer structure there. This space can never be used for anything in the building lifetime. Right? So that's why, again, one of these things, you have to go out into the world and see how things are done. It's just an example. Get inspired. See how things are done out there. If we look a little bit on geometry for buildings, again, this with if we remember that in Denmark, our tall buildings are actually ugly, right? Because we think that this is all Russian old buildings, but it's easy to make them look nice. It's not that big a difference. It's not that difficult. I'll just give some examples about how you can play around with the geometry of buildings. Both of these two buildings are actually from Dubai on the Sheikh Zayed Road. The first one over there, the columns are staggered each level here. So the one which looks like they're sloping, they're actually horizontally, and then they're staggered in. That's one way to do it. And then you have the other one. I think this tower here opened yesterday. It was the world's tallest tower, these two here. I think it was originally Emirates Airlines who, I don't know if they still have it. But there you can see they're playing with these slabs sticking out. So the columns are vertical, but the slabs are just cantilevering a little bit out. And then you can see how on the facade there that it actually just is cladded afterwards. That's a very buildable way to do it. Where the other one is a little more complicated because every beam reinforcement, every column reinforcement is different. Because it will have different loads, different lengths. So there's a lot of coordination which you need to put in when you build the building afterwards. Here is two other principles, and that is where the columns are sloping nicely out to shape the buildings. I think both of them look actually very nice, these two buildings here. But what you can see in the bottom is, see how already the car park stuff starts to become in. And that is just usual. And architecturally, this is a big challenge to figure out how to make that look nice. Right? Because I'm sure the architect doesn't like all these car parks, but it is a challenge every time you have a tall building. There's a lot of people there. This one here is actually one of my favorite towers. I have not been involved in it myself, but I like the simplicity of it. See, the columns are all running vertically down. So we have a nice, clean load path all the way down. Then the slabs in the bottom starts to get cantilevering out little by little as you go up. Very, very easy to build this one. And I think what they get out of it afterwards, this tower, which is actually doing like this, it doesn't look like it should be so simple. But I think this engineer has really thought out a very good structural system, very, very simple way to make the architect's dream come true. That's also what we have to do as engineers. This here is one of our own towers in Bahrain. These 3 towers here. Actually, we have about 10 towers we have done there. This is called Villamar Towers, and I forgot to say one thing before in the beginning about the course. A good structural engineer and a good mechanical engineer, when they sit together, then the core walls will take up about 20% of the floor plate. That's a good key number. On this one here, it's about 30% to 35%, the core size in the middle. The reason for this is that if you see how the tower is actually twisting up, and they're twisting the same way, all the columns. So that means if I have a column like this, and I have a load like that, I will also get a load which is horizontally. So each floor plate is trying to turn. So you're actually trying to screw all this building down into the soil. And to prevent this, of course, you need to have something which can hold back. And therefore, the core is a little bit bigger. And I also think that there's sometimes a frame running around the slab edge. But again, this is the architect's, vision. And of course, if the money is there, we should help with that. One funny thing you can also see here, if you just see what is happening a little bit further down, you have all these safety platforms, where this is usually also one of the things that if you want to work underneath where there's something happening on top, then it is actually possible, but you just need to do it right and take the right precautions. Let me just see here. I think I'll just take 3 more slides and then we can take a break, and then it'll be more Danish, with some Danish examples. If we concentrate a little bit more on the building itself, actually this one here, tower here, is called Index Tower. And this was done with my previous Australian company. And just to put things into proportion, the bottom part is about 40 stories, and this upper part is also 40 stories. The span in the bottom is 24 meters from fin to fin. And it's office and then residential. So all the columns, which is at the top half, does not continue down because we have a 24-meter span in the bottom. So at the level where you can sort of see there's a hole in the building, there we have this with a sacrificial formwork where there's a steel beam which can carry the self-weight of all the wet concrete plus a little bit more. So it was actually possible to build up without any temporary structures other than what was cast inside, you can say at the intermediate level. This was then repeated again at 80th floor later on. But this tower here is all the structure which is taking care of the stability is sort of outside the building. It's like a big H-frame which can take the load in both directions. The other 2 ones, these 2 here, is a little bit the same. The tall one, the blue one, I'll show you how, the whole footprint of the tower takes care of the stability. Same with the other one there, that's called a tube and tube. I'll not go in so much into this triangle here because it's a little bit about the philosophy when to do what and how to do it. But it's a matter of, if you have a small tower, let's say, and if there's no earthquake, up to 20 stories, then a core wall in the middle will be able to take the loads of the wind and the earthquake. But the problem is that as you go up in height, all of a sudden the core will be too little. So you need to go and grab the outer side of the wall of the building. So what we normally do when we design these towers here, if I say to one of my engineers, now you take this tower, the first thing he will look at is deflections and vibrations. That's the two most important things. When the deflection and vibration is there, then the strength, it's almost given it will work afterwards. That's usually how it is. So for these towers here, which is very, very non-Danish, is that you try to make the outer skin to work together with the core walls and the shear walls. I'll give some examples about how to do that. So first of all, when you have a building, all of you who are structural engineers, you know this, that the building has to be stable. They need to have walls which can take care of the loads. That's fundamental. And then the next thing we need to do is to put a core in the building. The core, again, a lot of architects ask me, okay, how big is your core? I don't know. It's your staircase, it's your elevator, and it's your mechanical. Then we put the wall around. So that's always what gives the size of the core. And of course, if it's in the middle, the core, the building will not be so susceptible for torsion. It will have very, very good load path for, for wind load. Also for earthquake. So of course, if you start to shift the core away from the center of gravity, then you will punish yourself with torsion. Plus, if you put it all the way outside, there is no load on it. So what's going to take care of the shear? So therefore, it's good to put the core in the middle. So you have gravity load from the slabs there. And avoid the, the torsion. Then there are some other fundamentals. I'm going to provoke a little bit today. You have these three wall, sections up here. And if you say the last one, this is how we have built in Denmark since 1972, where we have separate walls and then we don't do anything else. It's okay for low rise. But if you then look at the front one, and say, if we have one wall and we have the other wall behind, but it has the same geometry, but they are not coupled together. What happens then? What is the moment capacity of this wall? So if we call the first one 100%, then you can see, and you put the same force in the top, you can see the last one, it falls from 100 down to 20% moment capacity, turning over. But if you connect them with these link beams you can see in the middle, that the walls are connected with, these are called link beams, the one in the middle over each opening. It actually drops back up again to 75%. It's concepts and it's principles, but for all high-rise buildings, you will almost always have something called link beams. You want to couple the walls with each other. Again, it requires the right software. It's not rocket science, it's quite easy. But again, it's one of these things you have to get it in. Core wall size, okay, there's an opening, then we couple it with these link beams. Then, the next thing which happens is that when you have a shear wall and it deflects out, it's a little bit similar to when you have if you have a beam which is deflecting, it will always look like this. So we can put it up again, and then it'll just be a shear wall. A concrete frame, say we take out the shear wall, a concrete frame will be more like an S-curve. So you have the frame and you have the shear walls. Then when you start putting these two together, the frames and the shear walls, that is how it's almost always done like this. You get a very, very good, structure for stability. I found this little example here. This is a guy from, I don't know what his name is, ACOM. a company called ACOM in Southeast Asia, who did a little model and tried and say, okay, if I have a frame alone, I have a shear wall alone, and then I combine it, what do I get out of it? So we can always say, if I have a shear wall or a frame, I put a load and I measure my deflection. This is, what can we say? We can call this stiffness, right? This is Newton's first law. F equals K times X. And then measure what is actually the stiffness. You can see here the first one, he has done the thing, put a load and measured the, what's it called, the deflection, and then it gives a number. And he does it for the wall. And then he does, you can see the one called stiffness frame plus wall, where he models everything as one. You can see it's almost 3 times bigger than if you just added the two. I mean, frames and walls. So 2 plus 2 is not 4, right? 2 plus 2 is 8. It's a lot better to combine it. This example is, of course, exaggerated to make a point, because what if there's 3 walls of the red ones? Okay, it will look different, of course, but it's to bring out the point that we want actually to combine everything. See, what happens in a lot of these towers is that what we call frame, the yellow ones, columns and beams, that can also be the slabs, which can act as a frame. We grab everything which is there because it will move, it will shift. The upper one is the outrigger, which is a little bit the same, where you say at some levels you make a big solid portion, usually there are 2 levels, and you go out and grab the columns, and all of a sudden you have the whole building stiffness. You remember the blue glass building I showed before? That's done with the outrigger concept. I think let's take a little bit more. This is no. I think we can take the break now, and then afterwards. How long time do we have break? 10 minutes. Then we can jump back to this one here.